In this problem, we are given the circuit diagram here. We are told the voltage across the terminals of the 5 microfarad capacitor is 30, cosine, and our omega is 4,000 times t plus 25 degrees. This is in volts. We need to calculate the reactance, impedance of the capacitor as well, and then calculate the phasor current I, and write the steady state expression for our I once we found it. To start this off, we are going to do our x of c and our z of c. The formulas for these are in the notes linked below the like button in the description, and they're very similar. However, there's a little difference. So our x of c is going to be equal to a 1 divided by our omega times c. And our z of c, the only difference here is that we have a j in the bottom. So we have a 1 over j omega times c. Well, we need to flip the j into the numerator. So to do this, it's going to become a negative, and we will have a negative j divided by our omega times c. We know our omega is 4,000, and we know our c is 5 microfarads. So when we plug this into a calculator, it's going to look like this. We will have a 1 divided by our 4,000 times our 5, and a micro is equivalent to 10 to the negative 6. The only difference for our z of c is that we will have a negative j in our answer, so it's important to remember that. With this, we are going to get a 50. So our x of c is 50. Now we're going to add a negative j for our z of c, so we're going to get a negative 50. And that is how you would go about solving for capacitance and impedance of our capacitor. Next, we need to calculate the phasor current I. To find the phasor current, we are going to set I equal to the voltage over our resistance. And resistance is equivalent to the impedance. So this is really going to be voltage, which we are given up here, over our z of c. Our voltage, we can rewrite this as the polar form, and this is going to be 30 times our 25 degrees. We don't have to convert this or anything because it's in cosine. And this is going to be divided by our j times a negative 50, and this is because it is the z of c. Now, we want to divide our negative j50 out, so we're going to have to convert this top part into the rectangular form. To go from polar to rectangular form, we are going to have our number multiplied by the parenthesis, and then inside of our parenthesis we have a cosine of our angle plus the j times the sine of our angle with an ending parenthesis. This is going to leave us with approximately 27.2 plus j13. And this is all divided by our negative j50. If we divide these out, we are first going to get a negative 0.54 for the first part right here. But we want to flip our j up top, so it's going to be a negative j. And a negative times a negative is a positive, so we are going to be left with a positive j times 0.54. Now we are going to look at this part here. Our j's are going to cancel out, so we're just going to be left with a negative 13 divided by 50. Or 13 divided by a negative 50, and this is going to give us approximately negative 0.26. Now we have our equation here. We need to convert it to the polar form because it wants the polar form in here. So to convert from rectangular to polar, we're going to use that our v of m is equal to the square root of our real number squared plus our imaginary number squared. Our theta angle is equal to the tangent negative 1 of our imaginary number divided by our real number. And that is how we're going to solve for the polar form. Before we put this in our polar form though, it is important to note the angle. So we look at our rectangular form and we need to graph it. We know that our real number is in the x-axis and our imaginary number is the y-axis. Our imaginary number is positive, so it's going to be up here. Our real number is a negative, so it's going to be over here, meaning our angle has to be inside of this quadrant. Now we can actually plug these into the blue formulas and solve for our magnitude and angle. If we do this, we're going to get approximately 0.6 for our magnitude and an angle of negative 64.3. However, we can see that this negative 64.3 angle is going to be in our fourth quadrant. We need it in our second quadrant, so we're going to add 180 degrees to this. And if we do that, we're going to get approximately 115 amps. So I will reveal the answers for part C. We have 0.6 for the magnitude, like we said, and for the angle, we have approximately 116 amps. Now, to write the steady state expression, we know that our omega is going to stay the same throughout. So our omega is going to be the same here. Now, we found the magnitude for our I, it's 0.6. This is just going to be for this equation right here. And we know that our angle is also 116. So we'll plug this in here. And that is how we would write our steady state expression. And that is also how you would go about solving this entire problem. If you want more network analysis problems, there is a playlist in the description, and if you want notes for this material or the entire course, they will be in the description as well below the like button.